All right, so let's work on this problem. So I have a simple supported beam, pin, and a roller, and two individual concentrated forces, and they're all at L apart. So we're going to draw the shear force and bending moment diagram for this. So the first step in this problem is to find the reactions. Okay? So I want to draw a shear diagram, so I'm going to solve for the shear. So I know that on the left side, my shear at A, I'm going to draw positive shear at A. Remember, up on the left side, right? And positive shear at B on the right side is down. Do I have a moment at A? Yeah? But we know what it is. What is it? It's 0. It's at a pin. And at this roller at B, what is it? Also 0. So I really know already, before I even get started, that when I draw my moment diagram, I need to start with a moment of 0, whatever shape it takes. I need to land with a moment of 0. So I know my starting points. So let's find the reactions in terms of shear. So to do that, is this thing focusing in and out?
Yeah.
Like I take my hand away, it does something? Oh, yeah. Let me turn the light on. Maybe that'll help it. Does that, see if that, yeah, okay, that's what it was. It was lighting. Sorry. So I'm going to sum moments, and I'm just going to decide to sum moments at A. You could sum moments at B if you like. Make sure it's in equilibrium. I'm going to use right-hand rule. So summing moments at A, my two applied forces at P, what kind of moment do they create about A? Positive or negative? Negative. So I'm going to have minus P. The first one has a moment arm of L. The second one has a moment arm of 2L. So that takes care of the moment of my two applied loads P. So that's how you handle it, Mr. Patel. If you don't have numbers, you just use the symbols. So what's my shear force at B? What kind of moment does it create around A? It's also negative. And what's its moment arm? 3L. So when I solve for the shear at B, what do I get? I get negative P. So what is the shear force at B? Negative P.
Does that mean we assume correctly?
No. Yes, I assumed correct positive shear force.
Right.
There is no assumption for that. There is positive shear force, and it's down on the right side. So that way I know when I draw my shear diagram, what should my shear at B, what should that be? It should be negative P. So now if I sum forces in the y direction, I should be able to solve for my other reaction, which would be at shear at A. So again, I'm going to assume up is positive, make sure everything's in equilibrium. So looking at the forces, I have the shear force at A up, I have the shear force at B down, negative, and I have two forces P also acting down. So I put my negative P for B in here, and what's the shear at A? It's P. So what's the shear force at A? P. What's the shear force at B? Minus P. So I know when I draw my shear diagram, I'm going to start with what value for shear? P. And then when I get through to the end, I should get a minus P. So I know where I'm starting, I know where I'm ending for the shear diagram. Do I know where I'm starting for moment at A? Yes, the moment at A is 0. And whatever happens along the way, I better land back at 0 for B. So what I like to do is right underneath the problem, I like to draw like a template. So there's my edge of my beam left and right. And then through that, I'll draw a x-axis for how things vary along the beam. and I'll say that this is positive shear. And then I like to come over here and put the units, so I don't have to put the unit on every one of my numbers. So I'm just going to say, there's no units here, but let's just say it's going to be in kips. So now, I'm going to start with what I know. What do I know? Starting from left and working to the right, positive x-axis, I'm starting here. Do I know the shear at A? What is it? It's positive P. Why do I know it's positive P? Because I solved for it. What's the shear at B? Negative P. So I know where my shear diagram starts, and it needs to do something and land there. And if I don't land there, then I've done something wrong. I'm either constructing the diagram wrong or I made an error in one of my values. Now, what's our fundamental relationship? We know that the change in shear is equal to what? The load. We also know what? That the change in shear is equal to the integral under the load curve. These are the two fundamental relationships that I need to build my diagram. So let's start with this one first, the change in shear. So I know my shear is P here. Let's look at the load. What do I know about the load from 0 to L? What is the load from 0 to L? It's 0. Can you integrate 0? What's the area under a curve that has 0 height? 0. So it says the change in shear is 0 from 0 to L. So what should my shear be at L? Let me go ahead and add another line to my template right there at P. So what should the shear be just to the left there? P. Unchanged. Because the change in shear is 0. What's the shape of the curve connecting these 2 points?
Straight line.
Why is it a straight line?
It's got to connect.
It does have to connect, but I can think of a lot of lines that will connect those 2 points.
Well, your slope is 0.
Yeah, the slope of my shear diagram is equal to the load. What's the load everywhere? So what kind of curve has a 0 slope? Horizontal line. So there's my shear diagram for the first third of the beam. We also know that the change in shear is equal to the load P. So as I go from the left side to the right side, I am passing underneath a load P. Is that a positive load or a negative load? Negative. So I'm going to take my shear of P and I'm going to subtract P, and where do I end up? 0. So now I'm going to look from L to 2L. So let me put a line in for where that happens. I'm going to go back to my equation, or my relationship that the change in shear is equal to the area under the load curve. So here's the section I'm looking at. I go up, and what's the area under the load curve?
L.
0. There is no load. Well, it's 0. So if I start at 0 and I have no change, I have to end at 0. And what line connects those 2 points? Well, according to this, the slope of the shear diagram is equal to load. What's the load here? So it has 0 slope. Now as I go from the left side to the right side, I pass under my load P. How much does my shear change? P. And what's the value of P? Positive or negative? Negative. So I have 0 minus P brings me to negative P. So the change in shear between these two better be 0. Is that true? Well, according to this, the change in shear is the area under the load curve. And what's the area under my load curve here? Well, I have no load. So it's 0. So that works. And what's the slope of my shear diagram? Equal to the load. What's the value of the load from here to here? 0. So here's my 0 curve. And there's my shear diagram. Now that may not seem easier, but if I had to write equations for shear force, what would I have to do? I'd have to make one cut, draw a free body, a second cut, draw a free body and do equilibrium, a third cut, draw a free body and equilibrium. And how many calculations did you see me make doing this besides the reactions? None. Well, they're simple ones. They're in my head. You like that? We're going to do this a lot.
Shear is easy. Moments don't work.
No, it's exactly the same.
Moments don't work.
No, it's not. Don't listen to him. He doesn't know anything.
I could not get this instead.
So now I'm going to go down and do my moment diagram. So I'm going to draw positive x, positive moment, and these units would be force times length, kip feet. Now before we even get started, we know some moments. What's the moment at A? 0. 0. What's the moment at B? 0. So I know where I'm starting. Whatever my curve looks like, I know where I have to end. And what relationships do I apply? They look exactly the same as these, except the shape of the moment diagram is a function of the shear. I already have the shear. There's the shear. And the change in moment between any two places is the area under the shear diagram. So these are the two fundamental relationships. They're conceptually exactly the same as these, whereas the shear diagram is constructed with the load curve. We apply that same concept to construct the moment diagram. We do the same thing using the shear diagram. So let's do that. So I know where I'm starting with my moment. I want to know the change in moment over the first distance L. So the change in moment is the area under the shear diagram. What's the area of the shear diagram over L? It's a rectangle. What's the area of a rectangle? Base, L, times height, P. And that's a positive area. So that means I'm going to start here and I'm going to add what to it? PL. What's 0 plus PL? PL. What's the shape of the shear of the moment diagram? Well, it's equal to the shear. So what's the shear at this point? P. Positive P. What's the shear at this point? Positive P. What's the shear anywhere from 0 to L? Positive P. What kind of curve has a positive constant slope? A straight line. In fact, if I looked at it, it would have a slope of P to 1.
Can you repeat that step?
Which one? We're going to do it 3 more times. Let's try it again. Let's go to the next section and try it. So now I'm here at PL. I want to know the change in moment from L to 2L. Right? So according to my equation, the change in moment is the area of the shear diagram. So let's go up and see what the area of the shear diagram is from L to 2L. What is the area of the shear diagram? 0. So there's no change. So if I start at PL and there's no change, I should end at PL. And the slope of the moment curve is equal to the shear. What's the value of the shear from L to L over 2L? 0. What kind of curve has 0 slope? Horizontal line. Are you guys breathing? Seems really still in here. So what do we do the next time? We're going to do exactly the same thing. We're going to say, I'm at PL. What's the change in moment over the last link? The area under the load curve. What's the area under the load curve on the last link? It's a rectangle. Base L times height minus P. So the area is minus PL. So PL minus PL is... Yes! We've found our way home. We made it. We knew where we had to go, and we got there. That should make you feel good. Does it make you feel good? Makes me feel good. And what's the shape of my curve? It's given by the shear diagram. So what's the value of the shear diagram right there? Minus P. What's the value here? Minus P. What's the value at the end? Minus P. What's the value anywhere in here? Minus P. So it doesn't change. So we have a constant slope. And that slope happens to be negative P, given by the diagram. So there's my moment. There's my moment diagram. That may be coincidental. Does this look familiar to you anyway? Have you guys seen this kind of loading setup before? You all have. What's that? Do you remember the second freshman course where you made reinforced concrete beams? They were loaded just like that. You'll notice the maximum moment occurs in the area between the two supports. That's where your beams always broke, between the two load points. Remember that? Where was shear a problem? Out here in this zone. You know why? Because that's where there's the only place where there's shear. There's no shear in the middle at all.
I think you tell us this during the freshman.
I did, but I just didn't tell you how I got it. I said, you'll learn later. So, hey, here we are, later. I predicted the future. Not as anything of consequence, though, like the value of the stock market tomorrow. Something where I can make a lot of money and retire. See how easy that is? Should we do some more?
Yeah.
I think that'd be a good idea. All right, let's stop this one.